And the type of numerical techniques we are going to study in this course include what's called finite difference, finite volume, finite element, boundary element. So these four methods, each of them are suitable for different type of partial differential equations under different geometric and environmental conditions. These methods are going to convert or approximate a partial differential equation with equations that we can put into and solve in computers. So computers are good at manipulating numbers. And these methods convert differential equations, approximate them into equations that computers can solve directly. They can, for example, into solutions of matrix equations, AX equal to B. And then we are also going to talk about direct and iterative solution methods for actually solving this kind of AX equal to B equations. And many of you think AX equal to B is easy. If you know MATLAB or other packages, you can just solve with one line of code. In MATLAB, that's backslash. How many of you know backslash? Okay, that's good. In Python, it's linear algebra.solve. How many of you know that? Okay, so good. But the type of AX equal to B we may get in partial differential equations may be beyond the capability of backslash or linear algebra.solve. That's because they are so large. They can be orders of magnitude larger than the kind of even memory requirement of just directly solving AX equal to B. And that is why we will be talking about iterative solution methods for solving this kind of equations, which is a result of discretizing a partial differential equation using finite difference, finite volume, finite element, or boundary element method. So this class, the good news is that there is no exam, no midterm, no final. But don't be happy yet, because we have 8 project sets. And each project set can be a very exhausting or very time-consuming task. So these projects, they are quite different from the kind of homework assignments you may be used to in undergraduate studies. They usually require you to take a problem that is not yet very well formulated. So take a problem that may not be immediately obvious how to start, even go to solve it. And then you need to not only apply what you learned in class, but also you may have to try things yourself, or even go to the internet, look for solutions, or even look for papers and read what is in the literature to figure out how to solve the problem. Another thing is the amount of coding and debugging you may expect to do to solve these projects can be pretty intensive. That aspects depend a lot on how much experience you have on coding. So if you have written 100,000 lines of code in your lifetime, you probably don't really worry about that. But if you are new to programming, then it may take significant amount of time for you to just get familiar with being able to program a significant code starting from scratch to solve a problem. And on top of being able to write software, write code to solve problems, you should expect a huge difference between writing numerical code and writing regular code for other computer science applications. And this difference especially shows up in the debugging phase. So debugging a regular computer code is easy compared to debugging numerical code. Because debugging regular computer code, if something blows up or if something have a memory leak or something, you can procedurally, you can really, if you are a veteran programmer, you know how to trace the bug, find where it is. But debugging a numerical code not only requires the regular computer science skills, but requires a lot of mathematical reasoning. If your code doesn't really crash, doesn't really segmentation fault, but slowly goes to infinity instead of producing the answer you expect, how do you trace the bug? How do you find out which part of the code, which line of code is responsible for that slowly diverging to infinity or just producing an utterly wrong answer? That's very non-obvious. Developing that skill is a significant portion of this class. So especially in the beginning, expect to spend a lot of time developing that skill. And this is the most, by talking to students who took this class before, this is probably the single most challenging part of this course, is doing the projects and figuring out how to debug my code that doesn't produce the right answer. Okay. The worst thing you can do is to start the project too late, because you expect to write this amount of code, but the time it may take for you to debug it may be a lot longer than you need to write it. And the collaboration policy is on stellar, but in a nutshell, you are very much encouraged to discuss with each other, and that's why I have everybody introduce yourself to other people. So discussion, collaboration is very encouraged, but the outcome of the discussion should completely be in your mind. You're not supposed to type down stuff during your discussion and take it home with you. Absolutely no sharing of code or any documentation. Okay, so any discussion, you need to absorb the result of the discussion in your mind and code and write documentation, write the reports completely separately. Understood? All right. Okay. Any questions so far before we go into the technical portion of this lecture?